Okay, in today's and tomorrow's lecture, we will consider one topic which is very useful, very important in the domain of statistical signal processing and adaptive signal processing. You can call it, so you can treat these lectures as kind of appendix to our main lectures that ended in the last class. This particular topic, I repeat, it's very important in signal processing. It's called singular value decomposition. Singular value decomposition, that is SVD of a matrix, and pseudo inverse of a matrix, pseudo inverse. This is very useful in communication, control, signal processing. I thought this would be a good occasion to introduce the students this topic to the students. But before I get into this, then I have to derive certain properties of matrices and all that, which I will do today. In the next class, I will use these results to get into SVD theorem and its extension to pseudo inverse. Okay. We have already done some exercise on vector space theory. So, suppose I consider a finite dimensional vector space V and a linear operator T, which maps V to say another space V prime. That is, there is V and this is V prime over some field is either real or complex, and T maps it to some domain within V prime, we call it R. R is called the range, R is the range space. In fact, R will be a vector space, we will shortly see range space of T. That is, what is R? R consists of all vectors of V prime for which there is a vector in V, so that T working on that vector V gives you this vector in R. That is, R consists of V prime, where V prime is element of this, and so that there exists at least one V element of V with T V V prime. Okay, loosely it is this. This is a R is a vector space, because if you take say one vector V 1 prime, which is say T V 1 equal to V 1 prime, and again say T V 2 equal to say V 2 prime, V 1 V 2 element of V, and of course, V 1 prime and V 2 prime element of V prime, then C 1 V 1 prime plus C 2 V 2 prime, this is nothing but T of C 1 V 1 plus C 2 V 2. But this element, this is an element of V, that means this is an element of R, because R consists of all maps of V, that is any vector R consists of all those vectors of V prime for which there is a source in V. That is, you pick up any vector V prime from R, you must find at least one vector small v in capital V, so that T working on V gives you that V prime. Okay. Now, you understand here that if V 1 prime is part of R and V 2 prime belongs to R, then any vector, any linear combination of them also belongs to R, because you find another vector as an element of V, that is C 1 V 1 plus C 2 V 2, on which if T works gives you this. That means, this is closed, and therefore, this is a vector space. So, this is called range space. Dimension of this range space, dimension of R, in fact, I will call it R T, this range of T, we should call it R T. Okay. Dimension of R T is called the rank of the operator T. Similarly, there is another space that is important, that is called the null space of the operator T, that is null space N T N T is a subspace of V. N T consists of all vectors element of V, so that T V maps to 0, that is T working on those vectors maps to the 0 of V prime. So, if you collect all these vectors, then it also becomes a space, subspace, and it is called null space. It is a subspace because if you take V 1, V 2 element of N T, then obviously C 1 V 1 plus C 2 V 2 also element of N T, because if you apply T over this vector, T is linear. So, you can apply T over V 1 which is 0, T over V 2 which is 0, and the summation is 0, which means C 1 V 1 plus C 2 V 2 also belongs to N T, which means N T is a subspace and it is called a null space. Dimension of N T is called nullity of T, and we will show, this is a very elementary result, that for any operator T which takes a vector space V and maps it to another, I mean a subset of another space, subspace of another space V prime, and if dimension of V is given to be, the dimension of V is given to be say n, that is V has dimension n, finite dimensional, V has dimension n, then n is equal to the dimension of R T, that is rank, plus dimension of N T, that is nullity. That is rank plus nullity is equal to dimension of the original vector space V. That is very important. It is not difficult to prove, we can prove it. That suppose you start with the vector space V and there is this n. Okay. Let alpha I equal to say 1 2 dot dot R be a basis of n. Okay. That means nullity of T is R, because there is dimension of R. Then I can take one vector say alpha R plus 1 element of V and not element of N T, that is from within V, but from outside N, I would say N T. Then if I append alpha R plus 1 to this set, that is a linearly independent set we have seen. Okay, we have seen this exercise. You can call it W R plus 1 is the, you can say that alpha I equal to now 1 to R plus 1 is also a linearly independent set. This we have seen already. When we started discussing vector space, we have done this kind of exercise, that if you have this set of a linearly independent set of vectors, consider the space spanned by them, there is N T, take any vector from outside that, append that vector to this, so it becomes R plus 1 here, then again it is a linearly independent set, simply because the new guy cannot be written as a linear combination of these fellows, because the new guy is already outside N of T. And if you now consider W R plus 1 to be the space, the span of I equal to 1 to R plus 1, that is, then obviously N T is contained in W R plus 1. Then you take another vector alpha R plus 2 element of V, not element of W R plus 1. Okay, that is outside W R plus 1, but inside V. Okay, if you append this, then again append this to this set, then again there is I equal to 1 dot dot now R plus 2. This also Li linearly independent. You consider the span of this, call it W R plus 2, so on and so forth. So finally, this process will stop when R equal to, when you have got number of element in this set equal to the dimension of this vector space, that is equal to n. Then you get a basis. This continues. So finally, you get alpha I equal to 1 dot 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 n. Okay, and span of this span of this is nothing but V. So, this way you get a basis of V, but again there is nothing unique about it, because you are always picking any arbitrary alpha r plus 1, alpha r plus 2, just alpha r plus 1 should be outside N T, inside V, so on and so forth, but there is no fixed choice. We have already done this exercise, so there is nothing new and I am going little fast here. So, this is V. So, this way you can obtain a vector space, the basis of the given vector space V, one of the bases. Now, my claim is that if I now consider, I already know that if I apply T on alpha 1, I get 0, T on alpha 2, I get 0, dot 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 T on alpha, I get 0, because alpha 1 to alpha 1 belongs to null space of T. But if I apply T on alpha r plus 1, or if I apply T on alpha r plus 2, or dot 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 if I apply T on alpha n, what do I get? I get definitely some vectors belonging to the range space of T, and those vectors also will be linearly independent. That is what we can show easily. That is, if you consider T alpha I, okay, I from r plus 1 dot 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 up to n, these vectors alpha r plus 1, alpha r plus 2, alpha n, they themselves are also linearly independent, because they are part of a linearly independent set, that is basis. Given a linearly independent set, any subset of it is also linearly independent. So, if I do not consider from alpha 1 to alpha n, but consider from alpha r plus 1 to alpha n, then they are also linearly independent. On them, on each of them I apply T, I get T alpha I. T alpha I, it belongs to R T. Are these T alpha is linearly independent? Answer is yes. That is, if you take this, okay, maybe I put a bracket here. If you take this and sum, so I equal to r plus 1 up to n equal to 0, is it that the only choice, only solution for this is that C r plus 1 should be 0, C r plus 2 should be 0, dot 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 C n should be 0, that is all the coefficients should be 0 and no other choice is possible? If so, then it will be linearly independent. Okay. But this means, using linearity, it means T working on C I alpha I zero. That means belongs to null space of T, because T working on this vector is giving you 0, this works on null space T. But at the same time I know that alpha r plus 1 dot 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 alpha n, they are not element of null space, they are outside null space. Okay. So, the only, that is, if you consider, that means if you consider span of only these people alpha r plus 1 to alpha n, this span, because this left hand side vector is a linear combination of alpha r plus 1 to alpha n. So, that means this vector belongs to here, okay, it belongs to this span. But again, by this equation this belongs to N T, that means this belongs to the intersection of N T and span of this. The intersection between n of t and the span of this is only at 0, because each of these vectors I told you that lies outside n of t, and I consider their span, I call it, if I take their span and if I take it N T, the only way, only place where they can interact, where they intersect is 0. Therefore, C I, okay, that means this summation C I alpha I is 0, I equal to r plus 1 to n. But again alpha is themselves are linearly independent, that means C I equal to 0 for I equal to r plus 1 dot 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 n. So, that shows that these vectors T alpha I from r plus 1 to n. So, there are how many vectors? N minus r vectors, they are all linearly independent, though they remain in, they belong to R of t, they do not belong to V, they belong to R of t, they form a linearly independent set, fine. But what do we do with them? We will show now that these n minus r vectors which are linearly independent and which belong to R t, they are in fact a basis, they constitute what? Basis of R of t, which means dimension of R of t is nothing but n minus r, because total number of elements is n minus r here. To show that they form a basis is not very difficult. That is, if you take this is R of t, if you take a vector, say any vector, this is v prime, this is v, if you take a vector say v prime here, there must exist at least one vector v, so that t on v, t working on v gives you v prime, that is for each v prime element of R of t, there exists at least one v element of v, so that t working on v gives you v prime. But I already have a basis of this vector space v. So, I can write this vector as a linear combination of those basis vectors alpha I, and I will now go from 1 to n. So, v prime is equal to this. Now, using linearity I can apply t on each of the alphas, but from alpha 1 to alpha n they belong to the null space. So, t working on them will give you 0. So, essentially what you get is C I t alpha I equal to r plus 1 to n. So, earlier I have shown that t working on alpha I from r plus 1 to n, they constitute a basis of R t, they are a linearly independent set. And now I show that not only linearly independent, any vector v prime belonging to R t can be written as a linear combination of those linearly independent vectors. This proves that t alpha I equal to r plus 1 dot 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 n is a basis of R of t. That means, rank of t, which is the dimension of R of t, this is nothing but total number of elements in this basis, which is n minus r. Okay. What was R? Nullity of t was R, by assumption we took that to be R. This implies rank t plus nullity t is equal to n, which is the dimension of the original vector space V. This is a very important result. This is one result we will need, since I do not know your linear algebra background, I have to do all this by myself, otherwise I would have easily skipped this. What is the implication of this null space? Suppose I say that if t is 1 to 1, that is, it takes one vector gives you 1, say it takes v and gives you v prime, and no other vector gives you v prime, that is, v points to v prime and v prime points to v. Then the relation is 1 to 1, given v I can get v prime, and given v prime I can find out who generated v prime, that is v uniquely, and in that case we say t is invertible. Okay, that is, given v prime I know its mother, its origin, that is, on whom by working on t, by using t I could get the vector. Okay, so, t 1 to 1 and thus invertible if and only if null space, that is n t, consists of only one vector, that is 0, implying nullity of t is 0. This is very easy to show, that suppose it is given that n t consists of 0 vector, and this is v, this is v prime, say R of t. Okay. You take a vector v prime here. Suppose it is not 1 to 1, I have a situation like this, that there is at least a case like this, where there are two vectors v 1 v 2, which under t maps to the same vector. In that case, I will say that t is not invertible, because given v prime I do not know whether its inverse is v 1 or v 2, because more than one possibilities exist. So, it is not invertible there. Suppose we have a situation like this, that is t v 1 equal to v prime equal to t v 2. That means, if you take this and this, that means t of, using linearity, v 1 minus v 2 is equal to 0, which means v 1 minus v 2 belongs to n t. That means, v 1 minus v 2 is simply 0 vector, because n t consists of 0 vector by assumption, which means v 1 has to be equal to v 2. So, in that case, that means it is not possible to have two different v 1 and v 2. So, that t of v 1 gives you v prime, also t of v 2 gives you v prime, it is not possible. If it be so, then v 1 and v 2 must be same. So, given that null space consists of only 0 vector, that is nullity 0, T definitely is 1 to 1. Okay. But on the other hand, given that on the other hand, if n t not equal to 0 vector, implying nullity t greater than equal to 1, that is at least 1, that is it has at least one vector, I mean it has at least it is not, its dimension is not 0. So, that means it has many vectors, many non-zero vectors. Suppose it is so. If it is only having 0 vector, t is 1 to 1 we have seen. If it is not having only 0 vector, that is if its dimension is greater than or equal to 1, then also is it that you can have t 1 to 1? Answer is no, you cannot have, because for t any t v equal to say v prime, choose any u element of n t, so that u not equal to 0, and t v plus u will also give you v prime, because t u is 0, because u belongs to null space. So, therefore, v and v plus u, two distinct vectors, give rise to, after mapping, give rise to the same vector in R t, that is v prime, which means obviously t is not invertible. So, if n t consists of 0 vector, 1 to 1, if it is not, it cannot be 1 to 1. That means, t is 1 to 1 if and only if the null space consists of only 0 vector and nullity 0, which means rank should be same as the equal to n, that is the dimension of the original vector space V. Okay. Then only t is invertible. Okay. This we are doing in case of using this abstract notion of linear operator and all that, but in the case of matrices, because we have to now come to matrices, you consider a matrix A belonging to say real matrices M cross n. What does this do? A, it takes say n cross m, it takes r to the power m, that is real valued vectors of length m, it maps to r to the power n. How? Because you take the vector, then apply multiply the vector, pre-multiply the vector by a, you get another vector of length n. So, that is the relation, and that is of course a linear relation we all know. Okay. So, it is a linear operator working on R m give you R n. Okay. This is a special example of that case. In this case, what is R a? A is the operator. What is R a? Now, if you see a matrix, it has got a column say C 1, another column say not C 1, say call it A 1, another column say A 2 dot dot dot, another column say A, how many columns? M columns. Then if you multiply these, if you take a vector from R m say C 1 dot 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 say C m, then this is nothing but a linear combination of these columns. Columns are of length, these columns are of length n, n cross 1, the columns belong to R n. So, that means, what is the output vector? That is after this after this mapping or after this multiplication, you get a vector from R n. What is that vector? It is nothing but linear combination of some specific column vectors belonging to R n. What are the column vectors? Columns of this matrix. So, that means, R a is nothing but R a is what? Is given by, each element of R is given by linear combination of the columns of A. That means, the column space. What is the column space of this matrix? Set of all possible linear combinations of the columns of this matrix, that is same as the range space of this matrix, because in the range space if you pick up any vector, there is nothing but some linear combination of the columns, because when you multiply a vector by a matrix, by this matrix, you get nothing but linear combination of the columns as shown here. Okay. So, this range space consists of nothing but, is nothing but, range space is nothing but the column space of the matrix, I repeat, because any vector of range space is a linear combination of certain columns, okay, and these columns are nothing but the column vectors of this matrix. Okay. Now, some results relevant to SVT. You consider such matrix A belong to say as before R n chem n, then A transpose A and A, they have the same null space. This is theorem. That is, null space of A transpose A is same as null space of A. This can be proved easily. Suppose you take a vector, say V, from null space of A. That means A V equal to 0. V is of length m, 0 is a length n vector, because A is n cross m. But then, but this implies A transpose A, if it works on V, that also is 0, because A V is 0, is not it? That means, if V belongs to N A, then V belongs to N of A transpose A. This means, N A, this is very trivial, is contained in this, because any vector belonging to N A means A working on that is 0, and in that case A transpose A working on that also is 0. That means, that vector also belongs to the null space of A transpose A. But we have to prove the other way also, that left LHS is contained in RHS, and then RHS also contained in LHS. This is what we have to prove, and this is not difficult. You pick up firstly LHS and RHS, these two subspaces have one thing in common, that is 0. At 0 at least they have something in common, they are same. So, now pick up a vector x belonging to the null space of A transpose A, and x is not 0, because at 0 they are common. So, no point in taking up 0 here. This means, A transpose A working on x is 0, that means 0. Now, if I pre-multiply this by x transpose here also, I get scalar 0 here, but left hand side is A x norm square in the Euclidean norm sense equal to scalar 0. This is possible only if this is the 0 vector. You know, norm square is 0 or norm is 0 only if the vector is a 0 vector. This is 0 vector, which means x belongs to null space of A. So, then we prove that this null space of A contains this also. Okay. So, that means, we prove this. What is the implication of this? That we had a situation like this. This was under map A, and this was and under A transpose A, mind you, A transpose A is a matrix of size what? A was n cross m. So, it will be m cross n, m cross m. So, that means, it takes a vector from R m and gives to the vector, gives a real generates a vector from R m only. Okay. That is, while we know that range of A belongs to, range of A is a subset belongs to R n, range of A transpose A belongs to R m, but null spaces is same. That is, if there is a space, this is n of A equivalently n of A transpose A. Okay. So, under A, R m is mapped to R n, and there is a null space, and under A transpose A, you can show that this is mapped to itself, A transpose A mapped to itself, but this operator and this operator both have the same null space, this. Okay. Now, that means, what is rank of A? Rank of A is the dimension of this range space, and rank of A transpose, this is R of A transpose A. Okay. Rank of A means dimension of this range space. Okay. That is nothing but n minus, there is n, m minus, m is the dimension of R m, m minus nullity of A. And what is rank of A transpose A? That is the dimension of the space, which is equal to again dimension of the original space, that is same as m, minus nullity of this, and nullity of this is same as nullity of A. That means m minus nullity of A transpose A, that is rank of A transpose A. That means A and A transpose A, they have the same rank. Similarly, by the same, I will not do it. You can similarly you can do A transpose n of A transpose is same as n of A. This can be proved, implying rank of, sorry, this is A transpose, means rank of A transpose is same as rank of A transpose. And those who know elementary matrices, they know rank of A transpose is same as rank of A, and we have seen already rank of A is nothing but rank of A transpose A. This shows that A transpose A and A transpose, they have the same rank. Now, remember one thing, A transpose A and A transpose both are symmetric matrices, Hermitian, real Hermitian matrices, that is symmetric matrices. So, we have, they can be diagonalized, they have got a set of orthogonal eigenvectors and their eigenvalues are real and non-negative. Okay, they can be 0 or positive. This we have done on plenty of occasions in this course. Remember that both these, though the A transpose is of size n cross n and this is size m cross m. So, the eigenvectors are of different size, but this also has a set of eigenvectors A transpose A, m number of eigenvectors which are mutually orthogonal or orthonormal, and corresponding eigenvalues are real and non-negative. Here also we have got n number of eigenvectors which are mutually orthogonal and the corresponding eigenvalues are real and non-negative, mind you. In fact, we will show then that rank of such symmetric matrix is also given by number of non-negative eigenvalues. Okay. If an eigenvalue repeats, I will count it, if it repeats twice, I will count it as 2, and that way I will count the number of non-negative eigenvalues. Okay. But remember this. Okay. Now, again I will be going to the eigenvalue eigenvector side, and we all know what they are, but we have to do quickly. Again I will come back to this abstract notion of operators and all that, but this time T is working on V to V, and V is a finite dimensional vector space. Then small v, element of V is an eigenvector of T if V firstly is not 0 and T V is some scalar times V itself. That is, you work on, you use T on V, you get a vector in the same direction, just it is either amplified or attenuated by a factor lambda. Okay. Lambda scalar belonging to the field is called eigenvalue. Okay. Then W lambda, suppose set of all, that is mathematically you collect all elements of V, so that T V is lambda V. Then W lambda is not only a subset, we will see it is a subspace, it is called the eigen subspace belonging to lambda. How? Just simply if you see, if V is a eigenvector, 2V also is an eigenvector, 3V is an eigenvector, it is scalar multiple, because T on some constant times V, constant will go out, T the constant times T V, that is constant times lambda V, which is lambda into constant time V. So, that is an eigenvector. Okay. So, remember that eigenvector is not unique for an eigenvalue lambda. For each eigenvalue lambda, there are many eigenvectors possible. Suppose I consider all such eigenvectors belonging to the same eigenvalue lambda, and I give it a name W lambda. Okay. Then this is subspace, because if you take V 1 V 2 element of W lambda, then C 1 V 1 plus C 2 V 2, this also belongs to W lambda, because if you apply T on it, you can apply use linearity C 1 into T V 1, which will give you lambda V 1, and C 2 into T V 2, which will give you lambda V 2. So, lambda you can take common, again you get C 1 V 1 plus C 2 V 2, okay, which that means this fellow implies C 1 V 1 plus C 2 V 2 belongs to W lambda. That means, W lambda subspace is not just a subset, is a subspace called subspace corresponding to eigenvalue lambda. Okay. Now, we will show that if you have two distinct eigenvalues or several distinct eigenvalues lambda 1, lambda 2 dot say lambda r, the corresponding eigenvectors are linearly independent. We will show that, but before that, that is we want to show that if lambda 1, lambda 2 dot lambda r are distinct eigenvalues, then corresponding eigenvectors V 1, V 2 dot V r formal Li set, linearly independent set. We have to prove it. Now, before we prove it, some properties. 1. Suppose consider a polynomial. P of say anything, say t, just form a polynomial something like this, a 0 plus a 1 t plus a 2 t square dot say anything a q t to the power q. Then you form the polynomial operator p capital T, that is wherever you have got small t variable coming, just replace it by capital T, a 2 t square. T square means t followed by t, that is t square working on a vector means first work t on it, whatever comes again work t on it, so on and so forth, and a q t to the power q. Then you see one thing, if there is a vector t v equal to lambda v, then instead of t, if I apply this operator, polynomial operator p t on v, what I get is a 0 times v. So, a 0 plus a 1 times t v is lambda v. So, a 1 lambda, then a 2 t square v means first t v which is lambda v, again t on that means lambda square v. So, a 2 lambda square plus dot plus a q lambda to the power q v. I repeat again, p t, you replace p t by its expression, a 0 working on v means a 0 v, a 1 into t v means a 1 into lambda v, lambda comes here, a 2 t square v means a 2 t working on t v, a 2 t t v, t v is lambda v, take lambda out, t v again lambda v. So, you get lambda square. So, a 2 lambda square on v dot. So, you get this. So, this is nothing but same polynomial which we started with, but instead of t we have got lambda. So, p lambda v. So, if you have got a polynomial, if you want to operate in a polynomial form that works on an eigenvector, resulting thing is the eigenvector multiplied by the scalar, where you in place of the operator you replace the eigenvalue. This is one property. Another property is, another thing is that we are given lambda 1 not equal to lambda 2 not equal to dot not equal to lambda r. Corresponding eigenvalues are, eigenvectors are v 1 v 2 dot v r. We have seen it. Okay. So, I have to prove that if C I v I equal to 0, we have to show that each coefficient is 0, that is V1 to Vr there is linearly independent set. That is the objective of this theorem. I mean there is an objective to prove actually, that show that the eigenvectors corresponding to distinct eigenvalues they are linearly independent. So, I pick up those eigenvectors here V1, V2 up to R equal to 1 to R, form a linear combination equated to 0. I have to show that this is possible only if C1 equal to C2 equal to dot dot equal to CR equal to 0 and no other solution exists, then that will show that this is linearly independent. How to show that? Okay. So, I pick up from I equal to 1 to R a particular case, say M, say take M less than equal to R greater than equal to I. I will show that Cm is equal to 0, Cm is equal to 0, and then you can pick up M in to be anything from I to I plus 1 to I plus 2 to R. So, that will show that each coefficient is 0, because M is general. Okay. Suppose I form a polynomial P m t as this. Here I take lambda m minus lambda 1, lambda m, these are all scalar numbers, lambda 2 dot dot dot, lambda m, I go up to lambda m minus 1 and then I skip lambda, go for this dot 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 lambda m minus lambda r, and here again t minus lambda 1, t minus lambda 2 dot 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 t minus lambda m minus 1, and then t minus, just follow the denominator m plus 1 dot 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 t minus lambda r. What is the property of this? If you replace t by lambda m, what do you get? Lambda m minus lambda 1, lambda m minus lambda 1 cancels, lambda m minus lambda 2, lambda m minus lambda 2 cancels, all the terms cancel, you get 1. If you take any other lambda j equal to 0 for j not equal to m, and in general j equal to 1 to r, but not equal to m, then it is 0. So, I can always construct a polynomial like this. I have picked up a particular index m, I am looking at mth eigenvalue lambda m, the corresponding coefficient here is Cm, the eigenvector is Vm, I am focusing on that, keeping that in mind I construct a particular polynomial. Now, if on this equation, if I apply P m t on that, right hand side of course is 0, because this polynomial operator working on 0 vector will give you 0 vector because of linearity, and this is a polynomial operator. This is whether you have the operator as t or as a linear combination as in a polynomial form, linearity remains. So, P m t can be applied individually on V i's. Okay. That means working on V I, okay, equal to 0, but this means I have already proved one property. This polynomial working on V I means resulting thing is the vector itself multiplied by a scalar value. What is the scalar value? Instead of t, in place of t, put the corresponding eigenvalue. So, that means left hand side is C I P m corresponding lambda I times V I, and this is equal to 0. Okay. But P m lambda you have seen only when I equal to m, this is 1, otherwise it is 0. That means C m V m is equal to 0. So, one possibility is either V m equal to 0 or C m is 0, but V m is an eigenvector, by definition V m cannot be 0, that means C m is 0, and m you take as I or I plus 1 dot 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 up to r. So, each coefficient is 0, which proves that eigenvectors belonging to different distinct eigenvalues, they are linearly independent. That means, if t takes from V to V, okay, and you have got these distinct eigenvalues, lambda 1 dot 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 lambda say r, you form the corresponding eigen subspaces. eigenvectors belonging to W lambda 1, if you take a, you can form a, you can find a basis of this subspace, you can find a basis of W lambda 2, you can find a basis of W lambda so and so. And since these spaces, I mean vector from here W lambda 1, vectors from W lambda 2, they are all linearly independent. That means you can form a direct sum of them. Okay. If this direct sum happens to be same as V, then if this, then we say T diagonalizable. This is because suppose T is diagonalizable. Okay. This is because suppose W lambda 1, you have got a basis alpha 1 1 to say alpha 1 or W lambda 2. What I want to say is this: you can form a basis, if this is so, you can form a basis of V by taking one basis of W lambda 1, another basis of W lambda 2, dot dot dot, a basis of W lambda, just appending them. Okay. That will form a linearly independent set because it is direct sum, because I told you eigenvectors belonging to distinct eigenvalues, they are linearly independent. You are picking a basis already from W lambda 1, already from W lambda 2, you are just appending the basis. So, you get a basis for V. So, if on any vector in that basis you apply T, each vector is an eigenvector. So, you get nothing but that vector itself multiplied by the corresponding eigenvalue. That means this kind of operation. So, that means if you have, I mean if you take any vector V, small v belonging to capital V, write it as a linear combination of this basis, capital T works on that. So, what you have to do, simply capital T work on each individual basis vector, and the corresponding, since each individual basis vector is an eigenvector of some eigenvalue or other, you will get nothing but that eigenvector coming back multiplied by the corresponding eigenvalue. Okay. Now, this when I comes to matrices, then this will be further clear. Okay. But before I go to matrices, just one more thing I wanted to show, that suppose T takes V to V, okay, and you have got lambda 1, you have got suppose a 0 eigenvalue, and then lambda 1, lambda 2, dot 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 say lambda r. Okay. So, that means, and V is given to be, that is also T is given to be diagonalizable, that is V is nothing but W 0, direct sum W lambda 1, direct sum W lambda 2, direct sum dot dot dot, direct sum W lambda r. This is given to you. Okay. In that case, if you take any vector, small v element of V, T working on V, that will be what? That will be given by a linear combination of, that will be, for that first we have to find out the basis of W 0. Suppose this eigenvector value, this W 0, this has got a basis say alpha 0 1, alpha 0 2 dot 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 say alpha 0, total number is something maybe say m 0, W 1 has a basis alpha 1 1, alpha 2 1 dot 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 say alpha 1 m 1, then W lambda r has a basis alpha r 1, alpha r 2 dot 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 say alpha r m r. Okay. Obviously, you have got how many elements here? M 0, you have got M 1, you have got M r. So, M 0 plus M 1 plus dot dot plus M r should be equal to the dimension of V, because if you append the basis, all these bases, they form a basis for V that you have seen, because the operator is diagonalizable, because you have got this, and therefore, you have got this direction of decomposition of V in terms of this. But there is a difference between the eigen subspace W0 and the other ones. Eigen subspace W0 corresponds to the eigenvalue 0, other ones corresponds to distinct but non-zero eigenvalues. Now, if you pick up any V, element of V, you can write V as a linear combination in terms of these basis vectors. Okay. C I j alpha j I equal to I equal to 1 to m j, and then j equal to 0 to r. For j equal to 0, we have got this ones alpha 0 1, alpha 0 2, dot 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 alpha 0 up to m 0, and likewise. Okay. It is nothing, it is just notation and jugglery, but actually I am nothing but doing nothing but I am linearly combining them. If I apply T over V, then T can be applied directly on these vectors. Remember, for j equal to 0, you have got alpha 0 1, alpha 0 2, dot 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 alpha 0 m 0. T working on each of them will give rise to the same vector, but multiplied by 0 eigenvalue. So, they give rise to 0. So, I do not have to consider them. Okay, that means, I have to consider from here to here. Okay, I have to consider from here to here. That means, T v is nothing but from j equal to 1 I have to start to r, and then I equal to 1 to m j C I j alpha j I times, because T working on times the corresponding eigenvalue. Eigenvalue will be, just a minute, lambda I j, there are two indices, lambda I j, okay, alpha j I. So, this actually shows that range space of T, any vector belonging to the range space. Okay. Firstly, any vector belonging to the range space of T, that is nothing but of this form T v is nothing but a linear combination of the combination of whom these eigenvectors corresponding to the non-zero eigenvalues, and these eigenvectors form a linearly independent set, because I mean within W 1 itself it was forming a basis, means they are linearly independent. Within W 2 itself, other one was forming a basis of W 2, it was linearly independent, so on and so forth, and when I appended them, it is still linearly independent, because they corresponding to eigenvectors corresponding to different eigenspaces, they are linearly independent. That means, I got a set of linearly independent vectors, one set here, one it consists of these dot 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 these all appended. I got a set of linearly independent vectors, which are actually eigenvectors corresponding to the non-zero eigenvalue. So, that any vector of the range space is a linear combination of them. That means, range space is actually nothing but the span of all the what actually range space is nothing but this part. Okay, range space is nothing but this part, because any vector belonging to the range space is a linear combination of these vectors, that is the basis vectors of W lambda 1, basis vectors of W lambda 2, dot 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 basis vectors of W lambda r. It is a linear combination of them, okay, and they are already linearly independent. So, this part corresponds to range of T, R of T, and this part corresponds to null space of T, because any vector from there, if you pick up, okay, if you apply T over that, you get 0. Okay. All right. So, I stop here. In the next class, I will use these results and get into SVD. Thank you very much.